Welcome back. We are in the third section of Chapter 4 now. It is called Optimization and Modeling. Finding global maxima and global minima is often made possible by having a formula for the function that needs to be maximized or minimized. And the process of translating a problem into a function, so going from words to symbols, is called mathematical modeling. In the notes, I'm going to walk you through one example of doing this, and then the homework will give you a chance to do it on your own. So let's start with the setup for our example. In this example, a farmer has 2,400 feet of fence. He wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? So this is a maximization problem, right? We're making a rectangular field. We want to find what dimensions of this field give us a field with the largest area. In order to get a feel for what's happening, let's just look at a couple of possible fields. So let's say there's our river. We could make a field like this. Say that's 100. This is 2,200. So then the area would be 100 times 2,200, or 220,000 square feet. And remember, we know one thing. We know that the perimeter needs to add to 2,400 because that's how much fence we have. So here we've got 2,200 plus 100 on one side plus 100 on the other. So that has to hold true for all our scenarios, and it does. So next scenario, again, draw our river. We can do a better job than that. So in this next scenario, let's do one like this. We're going to say 700 feet there and 1,000 feet there. So our area, 700 times 1,000, or 700 thousand square feet. Okay, last scenario. Now we've got 1,000 there and 400 there. So our area is 1,000 times 400, which gives us 400,000 square feet. So what did we see? Well, we saw that shallow, wide fields and deep, narrow fields gave us relatively small areas. So there must be some sort of nice in-between. So now let's just think about things generally. So in general, we can get rid of our old fields there. So in general, here's what we've got going on. We've got the river, and we've got our field. Do a better job there. We've got our field. I'm going to label that X. That means that's also X. Label that Y. This is our area A. So we have that the area is A equal to X times Y, and that's what we want to maximize. It would be nice if we could write this as a function of one variable instead of two. So let's use the info we have to eliminate y from our equation. Well, we know that the perimeter has to add up to 2,400 because that's how much fence we have. So that means 2x plus y is equal to 2,400. Remember, we don't need any fence along the river, so only one y here. So that tells us that y is equal to 2,400 minus 2x. Thus, we have a new formula for area. Our area is x times y. We don't want y anymore, so now it's x times 2,400 minus 2x, or 2,400x minus 2x squared. And if we look closely at our area function, we need to think about this in context and kind of look at it and see what are our bounds. So remember, we had bounds on our functions in the last section. Well, area needs to be positive, right? I can't have a field that's negative 100 square feet. That wouldn't make sense. So I need to make sure that this stays positive. And A is positive, or rather non-negative. We'll say, just to be technical, A is non-negative when x is greater than 0 and x is less than or equal to 1,200. So you can kind of look at the function and reason this out, or graph it and reason it out that way. Graphing it is probably the clearer way maybe for us. So now that we have those bounds, we can be really explicit with what we want to do here. The function we wish to maximize is a of x, which is equal to 2400 x, 2400x minus 2x squared on the interval 0 to 1200. Well, to maximize, we need to find the critical points, because the max is either going to occur at the endpoints or the critical points. We already have the endpoints, so we want to find the critical points. First step in that is taking a derivative. So a prime of x is 2400 minus 4x, set that equal to 0 and solve. 2400 minus 4x is equal to 0. It means 4x is equal to 2400, which means x is equal to 600. Like I said, the max has to occur at either the critical point or one of the endpoints. Let's evaluate A at these 3 points and see where the max happens. A evaluated at 0 is 0 times 2400 minus 2 times 0, which is 0. A of 600 is 600 times 2400 minus 2 times 600, which is equal to 720,000. A of 1200 is equal to 1200 times 2400 minus 2 times 1200, which is 0 again. So clearly, we have found our maximum. To maximize the area, the farmer should build a fence that has x equal to 600 and y equal to 1200. And we can be a little more specific, we'll put units on that, so fence that is 600 feet by 1200 feet. And we can add, that will give an area of 720,000 square feet. So that's an example. It's pretty much the same process that we've been doing in section 4.1 and 4.2, but now we've added a new piece, which is you start with a word problem and you need to translate from the word problem into a mathematical formula. Then everything else is the same. Find a critical point, evaluate the function at the critical points and the endpoints, find the max or the min, straightforward from there. So I'm only going to walk through one example of this because every example is kind of unique. They all have their own context. But I'm going to give you a homework assignment that has a few different ones that you can try. And I really would encourage you not to wait until the last minute on this one because this is very much a you learn by doing it section of the book. So you don't want to be trying to rush through this on Sunday night. You'll definitely go better if you start it earlier in the week. So next time we'll pick up with section 4.4, families of functions and modeling.